Good morning, everybody. Today we're going to talk about limits. We're jumping right in. To start, we're going to start with section 2.2 of the textbook that none of you have and none of you have access to, but don't worry, I have access to it. And it's on the definition of limits. So if we're going to talk about definitions, let's go ahead and dive right in. So what is a limit and what is a function? We need to start with that. A function is what we're taking a limit of. A function is maybe y equals mx plus b. Maybe it's x squared equals y. Maybe it's x squared equals f of x. Anything like that. Anything where you have some sort of input, a black box happens to it, you maybe know what's going on, you maybe don't know what's going on, and something comes out of it. You'll be familiar with functions like sine and cosine if you took a trigonometry class. You'll be familiar with exponential functions and logarithmic functions if you took an algebra class. All of those are functions, and we can take the limit of a function. So suppose that your function f of x is defined for all values of x near a point a. So maybe a equals 1, maybe a equals 10 million. We don't know, we're just going to call it a for right now. If f of x is arbitrarily close, excuse the spacing error, to some value L for all values of x close to our point A, we write that the limit as x approaches A of f of x equals L. And we say that the limit of f of x, f as x approaches A is L. And you're maybe thinking, Emily, this doesn't make any sense. Or Emily, what does any of this mean? And the answer is that the best way to show you any of this is through examples. So that's exactly what we're going to do. So this is our very first example, and you might look at this and be very overwhelmed, but don't worry, we're going to talk through it step by step. So example 1 says, use the graph of f of x to determine the following values if it's possible. So it might not be possible. We'll find out about that in detail a little bit later, but we're going to start pretty easy, and we're saying, what is f evaluated at 1? So to do this, we look at the value 1, and we go up, and we see that our function is about at I'm going to call that 1.5. So f of 1 equals 1.5. And another question we can ask is now, well, what's the limit as x approaches 1? So now we're interested in values near 1, but excluding 1. So as we do that, we're interested in these values right here as we get close to, but we don't touch 1. And as we get closer and closer, we see that, well, we're getting right there to that 1.5 number again. So we're going to say that the limit as x approaches 1 of f of x equals 1.5. And you might think to yourself, hey, that's pretty easy. I can just go ahead and plug in whatever's going on. And maybe you can, maybe you can't. That is yet to be determined. So let's scroll on and do part B. So in part B, now we're looking at f of 2 and the limit as x approaches f of 2. So f of 2 occurs right here. You'll know from your study, you'll know from previous classes, your study of piecewise functions, that when we have an open hole, it's not including that point, but when we have a point bubbled in, it is including that point. So when x equals 2, f of x equals 5. And now, just like before, we're interested in the limit. So we're interested as we get close and closer to 2, but we don't touch 2. And as we do that, we get closer and closer to the value 3. So we say that the limit as x approaches 2 of f of x is equal to 3. Now you'll notice that, and this is pretty important stuff, you'll notice that f of 2 does not equal the limit as x approaches 2 of f of x. That can happen. That's totally fair game. As long as you know that this is a totally fair game thing to do, you'll be fine. So this is totally allowed. So now let's ask the question, well, what happens if a point is completely undefined, right? I'm interested in f of 3. Well, I just have this open circle, and at least from where I'm looking in this big picture, there's nothing showing me what x equals 3 equals. So in that case, we write that f of 3 does not exist. Or, because mathematicians are lazy, we use a shorthand, DNE. But because there's points next to 3 and next to f of 3, we can still evaluate its limit. So here again, we're looking for numbers as we approach 3, but don't touch 3. And we can see that we approach the value 4. We just don't ever achieve 4. And that's okay. And that just means that the limit as x approaches 3 equals 4. And that's it for example 1. So now that we have a better idea of what a limit is, let's be more specific. You saw earlier that I was drawing arrows, one from the right and one from the left, and that's pretty important. So now we're going to talk about one-sided limits. That is, we're only caring about a limit as we come from one direction and not the other. So this is a one-sided limit, and you might call it a right side limit. You might call it a right hand limit. I was taught right hand, so I'm going to use my right hand. Suppose f, your function, is defined for all x near a with x values greater than a. So we're just looking, we have a point A, we're just looking at stuff to the right of a. If f of x is arbitrarily close to some value L, for all x sufficiently close to our value a, with, again, all of our x values being greater than a, then we get the statement below, and we say that the limit of f of x as x approaches a from the right equals L. And if there's a right-hand limit, then there better be a left-hand limit. And you see we've got the exact same thing, but this time x is less than a, so it's values to the left-hand side. And it's the exact same definition of the limit, but this time instead of a little plus sign in our limit definition, we say a little minus sign. And that's how we know the left is going to be negative and the right is going to be positive. So let's do another example. This time we're working with a table of values. And a table can maybe be a little bit easier for you to see because you have concrete numbers that you're working with. So this time I'm interested in the limit as x approaches 1, and I'm going to do it in tabular form. So let's go ahead and fill out this table. I'm going to use my blue marker again, and when I say f of x evaluated at 0.9, I get 0.53. When I go one step closer, and this time we're taking a left-hand limit because we're approaching 1 from the left-hand side. Now let's evaluate at 0.99. I get 0.50. 0.999 is our x value, and that makes our y value 0.500. And that's going to be it for the left-hand side. Now we're concerned with the right-hand side. So let's do 1.01. what is f of x evaluated at 1.01? And the answer is 0.498. Well, what happens when we add another 0? We get 0.499. And what happens when we add one more 0? Again, we get 0.499. So part B says, what is a reasonable value for the limit as x approaches 1 of f of x? We can see that just from the left-hand side, our numbers are decreasing, 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 and they're getting pretty darn close to 0.5. End of story. Now let's look at our right-hand side. We can see that our numbers are increasing from 0.498 to 0.499 to, again, 0.499. And there's some more significant figures that I didn't bother to write because we can see the pattern and we can keep going with this. So what is a reasonable value for the limit as x approaches 1 of f of x? My answer would be 0.5. Now you may be tempted to add on more zeros, but that would be a question of precision and accuracy. And for me, I would prefer it if you include as few zeros as possible so that you can just say, this is the value that it's approaching. But you can definitely tell when we plug 1 into our function, we get a divide by 0 error, and we don't really know how to graph this function, so all we can do is look at a table. So finally, let's talk about one theorem. Just one theorem for today. We're not going to do anything too crazy. And it's theorem 2.1 from the textbook. If you ever get a copy of the textbook, you'll look in and you'll see the exact same thing I have typed here. But this is a hard and fast rule. So assume that you've got a function f and that it's defined for all values of x near a point A. It starts off just as our regular limit definition. Then the limit as x approaches A equals L if and only if the limit as x approaches A from the left of f of x equals the limit as x approaches A from the right of f of x. So an easy way to check, and we just saw, is that the limit from the left has to equal the limit from the right, or else the limit does not exist. So what does this look like maybe graphically? We've already seen what it looks like in a table. Let's see what it looks like graphically. So here I've got just some function that I've decided to draw in blue, and it looks a little bit like this. And we can clearly see that we're decreasing as we approach 1. At the point x equals 1, it's undefined. We don't really have anything we can do, but that's okay. And then as we go from 1 to 2, we're increasing. And this is linear on the left and linear on the right, so it's a pretty easy function for us to deal with mathematically. So let's ask the question, well, what is the limit as we approach x from the right-hand side? So we're interested in values as we approach 1 from the right. So from 2 to 1, we see that our graph is decreasing towards -2. So the limit as x approaches 1 from the right of f of x equals -2. And we can do the exact same thing, and we're asking you to do the exact same thing, but this time from the left. So from the left, as we approach 1, we're going from 0. Well, our function is decreasing, and it decreases to a value of towards 2. So we can say that the limit as x approaches 1 from the left of a function f of x is equal to +2. Well, let's go ahead and use that hard and fast rule that we just developed, and we know that the limit x approaches 1 from the left does not equal the limit as x approaches 1 from the right. So we can say, and these 3 little dots mean thus, that the limit does not exist. And that's it for limits today.